இல்லையே சார்.
Madam?
Yes.
Shall we start?
Yeah, sure.
Okay. Sadam sir, start.
Okay, sir. In the name of Allah, the most beneficent and merciful. Assalamu alaikum and good evening to one and all present here. It gives me immense pleasure to welcome you all on behalf of PG and Research Department of Mathematics for the international webinar on role of operations research in engineering. We would like to start the program with Qiraat by Professor A. Mohammad Akhil.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم قل هو الله أحد الله الصمد لم يلد ولم يولد ولم يكن له كفوا أحد صدق الله العظيم.
Thank you, sir. Now I request Assistant HOD of the Department of Mathematics, Dr. S. Suresh Kumar sir, to deliver the welcome address.
Good evening, everyone. It is obvious to feel happy to deliver a welcome address. I am also excited and feel blessed about this role. It gives me great pleasure to welcome our most respected and beloved principal, Dr. S.A. Sajid, to this webinar. I welcome you, sir. On behalf of our department, I thank our principal for encouraging us to conduct a webinar like this today. Next, I welcome Vice President of the College Union and Head of the Department of Chemistry, Dr. A.K. Ibrahim Sharif, sir, to this webinar. I welcome you, sir. I feel privileged and highly honored to welcome our resource person, Dr. Neha Atankar, an Associate Research Scholar at Anlinger Center of Energy and the Environment, Princeton University, USA. I welcome you, ma'am. In this occasion, on behalf of our management, principal, and organizing committee members, I would like to thank our resource person for accepting our invitation and agreeing to share our valuable time with us. I also welcome our head of the department and convener of this webinar, Dr. Sheikh Mohammad Rafi, and coordinators, organizing secretaries, and organizing committee members. I welcome you, sirs. Finally, I welcome all the faculty members from various colleges, research scholars, and student participants. This international webinar organizes with an intent to know how operational research plays a vital role in the field of engineering. I am sure that you will feel enriched with knowledge after the completion of this webinar. With this, I conclude my speech. I welcome you all once again. Thank you.
Thank you, sir. Now I request our Vice President of College Union, Dr. A.K. Ibrahim Sharif sir, Head of the Department of Chemistry, to deliver the inaugural address.
Assalamu alaikum. Good evening. Respected Principal Sir, respected HOD of Mathematics, learned resource person, beloved colleagues, and my dear students. It gives me immense pleasure to deliver the inaugural address today on this auspicious occasion. Today's topic of the international webinar is operation research in engineering. The main aim of operation research is to apply developed analytical methods to help make better decisions. A significant feature of operation research is its overall look at the system and trying to improve it as a whole instead of focusing on one or more system components. Finding the optimal solution based on the type of problem and study through the use of operation research plays a major role in the decision-making process. Because of this, most planners turn their attention to this novel technique of operation research. In operation research, problems are broken down into basic components and then solved in defined steps by mathematical analysis, mathematical solutions. Operation research can be applied to a variety of uses, for example, scheduling and time management, urban and agricultural planning, enterprise resource planning, supply chain management, inventory management, network optimization and engineering, risk management, etc. With this, a brief introduction, I thank the organizers for giving me this opportunity and hope the participants will make use of this webinar and wish the international webinar a grand success. Thank you.
Thank you, sir. It is our privilege to introduce the resource person. May I call upon Mr. M. Muhammad Salih Mukhtar to introduce the resource person.
In the name of Allah, the most beneficent and the most merciful. Good evening to everyone and a warm welcome to all of you at this wonderful occasion. Really, I am very happy to introduce today's chief guest, Dr. Neha Patankar, Associate Research Scholar and Legal Center for Energy and Environment, Princeton University, US. She has done BE in Mechanical Engineering in University of Pune, India in the year 2010 to 2014. Then she has completed Master of Operation Research in North Carolina State University, US in the year 2014 to 16. Then she has completed PhD in the field of Operation Research in the same North Carolina State University, US in the year 2019. Then she has completed postdoctoral research in Princeton University in the year 2019 to 20. Right now, she is working as Associate Research Scholar and Legal Center for Energy and Environment in Princeton University, US. Research experience, she has concentrated more on research so that she served as different roles, such as postdoctoral researcher, research assistant, power genome developer, Gen X developer, Temua developer, and so on. Her interested research area mainly macro-scale energy system in the background of operation research. She is ongoing 3 projects. One is New Jersey role in the deep decarbonization of PJM, funded by PSEG. Second one, PJM rapid decarbonization through 2030, funded by Community Energy. Third one, electricity system capacity expansion and operational modeling, evaluation, and optimization of flexible carbon capture and sequestration system, funded by ARPAE program of DOE. Apart from that she is being the reviewer of some journals, and also she has published more than 10 papers in most reputed journals. Her research profile is very long, but I have given some important notes about her. You can refer her website. Such an eminent person is today chief guest. I welcome Madam and thanks for accepting our invitation with your busy schedule. I hope her session will be interesting and useful to the audience. Thank you, everyone. Thank you, Madam.
Thank you, sir. Now we hand over the session to our resource person, Dr. Neha Patankar, Madam.
Thank you so much, everybody. Thank you so much for joining. I am, Professor Sali said, I'm Neha Patankar, and today I'm going to talk about how operations research methodologies are currently being used to make decisions on a country level and how those decisions can be influenced through different solution methodologies. So for my presentation, I'm going to have to share a screen as it is a PowerPoint presentation. Is there any way that I can share my screen?
Yes, ma'am.
Okay, can you see my presentation well?
Yeah, yes.
Okay. All right. Thank you once again for joining. And before jumping into the main talk, let me give a brief bit more about my introduction and background. So as Professor Sali said, I have done PhD in operations research. But during that PhD, I had 4 advisors, one from electrical engineering department, one from civil and environmental, one from economics, and one more from industrial engineering department. So all of their combined knowledge and guidance has shaped my understanding about how operations research can be used in many different aspects of our world. So in my research, I use methods from the operations research literature and applied economics to evaluate how our energy system may evolve in the upcoming years. So I just want to mention before we start the presentation is that if you have any questions or concerns or did not get some concept, then please feel free to write your message or question in the chat so that I can get to it at the end of the presentation. Okay, so first, let's talk a bit about operations research methodologies. So what OR methods are essentially a set of analytical tools that help us solve different problems better. They are used in different levels of industries and different levels of organizations. How human beings are making decisions in the past are based on intuitions, right? So these methods essentially help us test our intuitions and provide a quantitative feedback to make decisions. The reason why these methods are so helpful in today's world is because the cost of performing this analysis or the cost of performing optimization analysis is much, much smaller than the potential cost of making a wrong decision or making a decision that has a higher cost than a potential least cost or optimal solution. So today, I'm going to explain this methodology, one of these methodologies, through a very, very simple example to start the talk with. And then I'll jump a little deeper into my research. So let us all consider just a very simple example of one very far island, and that is very far located from the mainland, right? Let's assume that there are a few people living in there, but person A owns that island, right? And that person is responsible for supplying electricity to everyone else on that island. So person A can use gas generator, they can use wind turbine, or they can use solar PV to satisfy the electricity demand. Now, for simplicity, in the first step, let's assume that tomorrow is going to be sunny and person A knows that for certain. So if it is going to be sunny, then, and if person A uses all wind turbine, then their profit is going to be minus $10, which is equivalent to $10 of loss. If person A uses all solar, then the profit is $60. And if they use all gas generator, then profit is $50. Now, since person A wants to maximize the profit, our brain instantly knows that they should be using all solar PV because that will lead to highest amount of profit. But what our brain did is essentially solve an optimization problem where X1 is a fraction of wind turbine usage, X2 is a fraction of PV usage, and X3 is a fraction of gas power plant usage, right? So assuming that they want to maximize the profit, the objective function of an optimization problem becomes minus 10, which is the profit from wind turbine, multiplied by the X1, which is the fraction of wind turbine. And similarly, we add profit of solar turbine, solar PV, or profit from gas turbine, subject to the fraction of each of these resources should add up to 1. So X1 plus X2 plus X3 adds up to 1 here, and the fraction cannot be non-negative, cannot be negative. So Xi should be greater than or equal to 0 for all I, 1, 2, and 3. So that is for all generators. So if we mathematically solve this problem, we get an answer that says that X1 should be 0, X2 should be 1, and X3 should be 0, which means a mathematical problem will also tell us to use all solar generators and maximize our profit to $60. Now, let us add a little bit more complexity to this problem. Let's keep the original formulation the same. But let's say that person A does not know whether it's going to be sunny or whether it is going to be windy tomorrow. So if it is windy, then wind turbine is more profitable. And if it is sunny, then solar PV is more profitable. So we know the profits of each turbine if it is sunny. And let's give some profits of all generators if it is windy. So as you can see, if it is windy, then of course the wind turbine makes more money, which is $100 here. If it is windy, then solar PV does not make as much money. It is $10 here. And gas generator, since it does not depend on the weather, the profit, irrespective of the weather, remains the same. Now, since as we can see that wind turbine has the maximum profit from wind turbine and solar PV is higher than the maximum profit from gas generator. So the initial intuitive answer is to use maybe, let's say, half wind if it is windy, if it turns out to be windy, and maybe let's use half solar if it turns out to be sunny. So what I want you to do is hold on to that thought that says, let's use half wind and half solar, right? So what we do next is calculate the expected profit of each turbine. So for wind turbine, if it turns out to be windy, our profit is $10. And if it turns out to be sunny, our profit is minus $10. Now, assuming that the probability that tomorrow is going to be windy, the expected profit of wind turbine is P multiplied by the profit if it is windy, plus 1 minus P multiplied by the profit that it is sunny. So P multiplied by 100 plus 1 minus P multiplied by minus 10, right? So what we do here is calculate the expected profit of wind, expected profit of solar, and expected profit of gas. Now, as you remember, our intuitive answer was to use half wind and half solar to satisfy the electricity demand. So our total expected profit would be 1/2 into expected profit of wind plus 1/2 into expected profit of solar plus 0 multiplied by the expected profit of gas. So, which turns out to be $22.5 plus $17.5 plus 0, which is $40, right? So the question now is this an optimal strategy to use half wind, half solar? So as some of you might have already guessed, as we can see here, if we just used gas turbine or gas generator, our profit would be $50, right? So if we use only gas turbine, then the expected profit is 0 multiplied by expected profit of wind plus 0 multiplied by expected profit of solar plus 1 multiplied by expected profit of gas, which turns out to be 50. What we learn from this is the expected profit in behaving optimally is 25% better than our initial intuitive solutions. So what we just saw was a classic example of two-stage stochastic programming problem, which is one of the operations research methodologies. We learned that the decision that person A took today, the profit that they expected changed based on what happens tomorrow, based on whether it is sunny or whether it is windy tomorrow. We learned that our intuitive solutions are not necessarily the best options. And we learned that the best decision of today, when faced with several different outcomes for the future, might not always be equal to the average of the decisions that would be best for every future outcome. So this figure here summarizes the concept very well, which says that the state of this person that has been taking this path, at their average position, they are alive, but the average state of this person might not be, right? So it just shows that the uncertainties in our system do affect our optimal decisions. So this methodology also lets us calculate the expected value of perfect information. That is, if a fortune teller comes to person A and tells them that, yes, I'm going to know exactly what is going to happen tomorrow, then it tells us the expected value or the value of that information to person A. And it can be calculated using this formula here. It also tells us the expected cost of ignoring uncertainty. So if person A says that, okay, I don't want to get too much into the analysis, I'll just make my decision based on my guesses. So it also lets us calculate the expected cost of ignoring or guessing the wrong choice, right? So here I am showing that I will not go too much into the details about the calculations, but for the example that I showed, the EVPI, which is expected value of having a perfect information about tomorrow, is $30, which means person A will be willing to pay at most $30 to somebody who knows the perfect information. And ECIU, which is expected cost of ignoring uncertainty, is $10, which means if person A decides to hire an analyst like me, then they will be willing to pay me at most $10 to understand the optimal solution. If you want to know more about this example in depth, then I have included some more details on this website. All right, so now that we have gone through the basics of operations research and one of the basic methodologies, let me give a bit about my motivation behind doing the research that I do. So as we know that India intends to achieve 500 gigawatt of installed capacity through non-fossil fuel resources, and 50% of its energy requirement it aims to satisfy by renewables by 2030. So because of this ambitious target, many sectors of our economy are expected to undergo drastic change in the next few years. But especially the power sector, the electricity sector, is going to undergo major change in the next 10 years. So as you can see here, time period going from 2015 to to 2050 on x-axis, and installed capacity of different generators such as wind, solar, coal, or nuclear on y-axis. This is the total capacity in India. So as you can see here, we are currently at 400 gigawatt of installed capacity. And even in the base case scenario, which considers that there is no further policy additions, we expect to see increase in power system capacity by 3 to 4 times in the next few decades. So because of this imminent change in power system, usage of many different resources is expected to change. And many different actors in the system, like you and me and policymakers and stakeholders, are going to need to work together despite our conflicting objectives. Now, because of these conflicting objectives, we expect to see some trade-offs in our system. So we have seen an ecological trade-off due to solar PV development. We have seen trade-off between water quality and emissions. We have seen trade-off between cost and weatherization of electricity system in Texas. And we expect to see many more such trade-offs in the coming years. So in my research, I use optimization-based models that consider conflicting objectives of different decision makers to provide robust technology deployment pathways. I use macro-scale energy system models that have 3 main components. First is an engineering layer that considers workings of different power plants and end-use technologies such as light bulb or electric vehicle or general vehicles. It has second layer, which is economic and behavioral layer that considers technology and fuel cost of different power plants and technologies. And it also considers preferences and priorities of different actors in our system. Third is a regulatory and policy layer, which considers economic regulation, market design, and energy and environment related policies. So for the rest of this talk, I'll go through a methodological framework. I'll present a case study that demonstrates the usage of this framework. And lastly, I'll talk about future research plans. So for case study, I'll talk about how land-related trade-off can be understood with OR methodologies, since renewable development is growing rapidly in the US. Okay, so let me jump into the modeling framework. I again tell you that if you have any questions, please feel free to just put it into a chat box and I'll be sure to get to it in the end. Okay, so in my research, I use capacity expansion models. During the PhD, I focused more on the energy system models, where we have primary energy sources such as gas and coal on the left-hand side. And we have end-use energy sources like transmission, residential heating, residential cooling on the right-hand side. And these primary energy sources are converted to secondary energy sources like electricity. And secondary energy sources are converted to final energy demands through various technologies and processes. So the objective of these type of models is to minimize the total system cost such that energy balance and process balance is met and final demand is satisfied. During my PhD, or during my postdoc, I mainly focused on the electric sector part of this entire large energy system model. And I have co-developed a model called GenX, which is based in Julia and Jump platform. So in this model, we have levels of network. We have 4 levels of temporal constraint, and we have 5 levels of operational details. So usually I use multi-zonal model, so where a country is split into multiple zones. I use representative hours, which means we cannot consider an entire year due to computational complexity. We can consider only a few parts of that year. And I use relaxed unit commitment constraints, which are, if you have thermal power plants, you have to figure out when to shut them off or when to start them. So those are in the unit commitment constraints. Okay, so here I'm showing an objective function of this GenX model. Don't worry about too many details here. I will roughly show you what they are. So first line considers the investment and fixed cost of different power plants. Second line considers the investment and fixed cost of installed energy storage capacity. Next, we have investment and fixed cost for charging power capacity. Then we have variable and fuel cost. We have cost of non-served energy. So sometimes the electricity goes off and there is a cost associated with that load shedding. So it is considered here. Then there is a startup and shutdown cost. So if you have a large thermal power plant or coal power plant, you need to pay some money to start it up or shut it down. And then lastly, we have transmission expansion cost. So this cost minimization objective of this GenX model, which can also be thought of as a social welfare maximization problem, gives us 5 different things. First, it tells us when and where to invest in electricity generation capacity. It tells us how to dispatch and operate that capacity. It tells us which consumer demand segment we should serve and which we can curtail. It also tells us how to cycle and commit the thermal power plants. And lastly, it tells us when and exactly where to invest in additional transmission capacity. Okay. So on the top of this basic optimization model, I have also added a few more components to make these models more useful in country-level decision-making. So the first step is that I have added geospatially resolved inputs, which considers 60 GIS layers, right? That tells us about the area which has maybe water bodies, existing infrastructure like buildings, schools, roadways, prime farmlands, national forests, state forests, or any other such land where we cannot physically build new renewables or transmission lines, right? So based on this GIS analysis, we get candidate project areas for wind and solar. That is, you can think of it as 4 by 4 kilometer squares in the entire country that are eligible to build. Then I calculate the levelized cost of electricity for that candidate project area, which is split into the cost of solar panel or wind turbine itself and the cost of delivering the electricity from those renewable resources to their delivery locations, such as small cities or large cities. Now this second part, to compute the second part, we need to go through 3 steps. First, we need to figure out a routing. That is, we need to figure out the exact route that the transmission line will take to connect the CPA to the delivery location. We need to calculate the cost of that route, and we need to adjust the cost based on different characteristics of the transmission line. So here I am showing a routing cost layer. So for those of you who might not be familiar with cost surface data, you can think of it as a very large data frame that has cost of each pixel on this map saved up. And we assign the cost based on a slope of that land, based on the terrain of that land, based on exclusion layers. So as you can see, the exclusion layer is high, a multiplier is high. So if there are some large cities, or if there are some ecologically important areas, or if there are some towns that may not want to have transmission lines through them, then we can physically increase the multiplier for that area to avoid new build through that area. So what operations research helps us do is to get the cost of all of these pixels, get the location of the candidate project area for solar or wind, and find a sequence of the pixels that can connect the candidate project area to their delivery location at the least possible cost. So we are running another optimization problem here to find the best routing for each CPA. Next, we calculate the cost of that route based on the actual cost layer. And then we adjust the cost based on various different aspects of the transmission line, such as length of the line or the voltage class or capacity or the grid time cost or even the right of way cost. Because when you create a transmission line, you have to buy a land around it, and it has a cost associated with it, which is in the right of way cost. So now that we have all of these geospatial inputs at a very, very high resolution, I put all of that into another tool that I developed called PowerGenome, which also takes into consideration other details of the existing electricity infrastructure. So it takes into account data about existing generators, renewable generation profile, cost projections for new renewables, or effect of new technologies such as electric vehicles on electricity demand. And what it does is it takes into all of this data at a much higher resolution and compresses it and puts it into energy system or power system model that I talked about a minute ago. What we do is we keep the linkage between a very resolved or detailed data and the aggregated cluster, so that when we solve these models and get the results at the aggregated level, we can map them back to the geospatially resolved inputs. So as you can see here, the blue ones show wind farms, or we can see the transmission lines on this map. And lastly, I find out the impact of this renewable development on different aspects, and I have mainly worked on understanding the land-related impact. Okay, so apart from this power system and energy system models, I have also developed a few different operations research methodologies that are beneficial for understanding different types of questions in these models. So there can be questions such as, do we need a planning strategy under different types of uncertainties? Do we know different objectives of different actors in the system? Are there too many uncertain parameters, right? So based on the answers to these questions, I use techniques such as stochastic programming that I described ago. I use Monte Carlo simulation or robust optimization or many other such methodologies that are demonstrated in the operations research literature. So overall, all of the research that I do can be divided into 3 parts. 1, I try to understand how deep decarbonization policies, that is policies that reduces emission, can affect power system development. In that first category, I have worked on several different projects over the last few years that try to understand the effect of these policies in California, in the entire US, and in PJM. I have recently modeled a Build Back Better Act in the US, which is the $1 trillion infrastructure package, and try to understand how that would affect the power system development. Second, I try to model advanced technology options. So as you can see, there are different technologies evolving right now that capture the carbon from the atmosphere and put it into land. So I try to understand how they might fit in our power system. And third, I try to understand the uncertainties and trade-off in technologies and resources in different aspects of our energy system. If you are curious about any of these projects, I would be very happy to answer your questions. But for today's talk, I'll go a little bit deeper into this project that shows one of the operations research methodologies in more detail. Okay. So this project tries to understand land-related trade-offs. And for that, I have created a spatially, temporally, and technologically detailed power system model for the western part of the US, which is west of the Colorado. So the objective here is to minimize the total system cost, subject to a constraint that says that we teach modeling to generate alternatives that tries to find maximally different portfolios which all have similar system cost so that we don't have to pay anything more, but they provide different technology portfolios that may satisfy different answers to different communities. So to visualize it in two dimensions, let's consider variable x and variable y. And f here is a feasible space, that is a feasible set of combinations of x and y. This point here shows the optimal solution of this problem given c as a cost vector. So this f1 here shows the area in the feasible space that is near this cost optimal solution. So what this methodology does is it finds the extreme point of these near optimal feasible region. So let's say again we have a minimization problem where c is a cost vector and x is a decision variable. Subject to ax equal to b, this is a hypothetical problem, so I'm not putting numbers here, and x greater than equal to 0. And let's assume that x1 is an optimal solution. So the first iteration of MGA becomes maximize the absolute difference between a new solution and the previously obtained solution, subject to a budget constraint. So a cost of a new solution has to be less than or equal to cost of the previous solution plus some delta. So let's say that x2 is an optimal solution to this problem. Then the next iteration becomes maximize the absolute difference of a new solution from both the previously obtained solutions. So one by one, we try to find the extreme points of this near optimal feasible space. Now, there are many different algorithms. The problem with this initial formulation is that we have absolute function in the objective, which makes this problem very, very difficult to solve. So to solve this problem approximately, there have been many different algorithms in the literature. And I use a modification of one of those algorithms that try to change the direction of this C vector to find different extreme points of this near optimal feasible space. So I minimize beta into x, where beta is a random coefficient for k iterations. And for each of those iterations, I solve the xk as an optimal solution. I solve the same problem with a maximization objective and gather the set of all of the solutions with maximization and minimization objective into a set called xall. Then I plot a cumulative area of the convex hull, that is, if we find it will be an area of a convex hull. If you find one more solution, then the area of that convex hull will increase, right? So area keeps on increasing until it flattens in the feasible space. Okay. So using this methodology, the first question we ask is, how many solar and wind sites are cost effective in the American West? So what we learn here is that the dark spots that you see here are the wind and solar sites that are chosen in the least cost solution. But the lighter areas here are solar and wind sites that are within our budget, right? So we learned that the cost-effective solar and wind sites are 3 to 4 times more than the solar and wind sites that we need to reach the zero carbon electricity supply in 2045. But the common misconception is that the world has a lot of wind and a lot of land for wind and solar, and we should just build them wherever, which turns out to be untrue. And we learn that less than 10% of all suitable land for wind and less than 5% of all suitable land for solar is cost effective. Next, we learn if there are any riskier characteristics of these sites, right? So we find 3 types of riskier characteristics based on the distance of a site to their delivery location, which means the longer the distance, the longer transmission line we are going to need and more potential of conflict. Second is based on human modification index. So this lower the human modification index, lower previous human activity on that land, which makes it ecologically important. And third is based on population density. So if you build a solar farm in a city, that place might have alternative usages and may have more conflicts than expected. So we find that there are more than 50% and more than 85% of wind and solar sites that have riskier characteristics. And we must use operations research methodologies to understand the trade-off when building wind and solar resources. So what we do is, from those MGA solutions, we find a solution that satisfies different objectives. So we may have an objective that maximizes, let's say, hydrogen storage, which has been in the news quite a bit recently. We may want to use wind farms in our backyard. Land types change significantly as you look from top to bottom here. The total risky build area in different types of riskier land changes significantly. But we also learned that the riskier build area cannot be reduced, or we cannot completely avoid it in order to reach our policy goal of zero carbon electricity by 2045. But we can look a bit deeper and see what else we can do in order to achieve that goal, but perhaps not build so much on the riskier lands. And we find technologies, carbon capture and sequestration, biomass, geothermal, nuclear, then that helps us reduce the new development on the riskier land. Okay, so now that we know that we cannot completely avoid new build on risky lands, we want to know if states can act to get capacity of solar and wind in the least cost solution as bar plots. On y-axis, we have different states in the US, and the error bars here show how the capacity can be increased or decreased without increasing the total system cost. But what we learn here is that if we try to reduce a new capacity build out in one state, let's say California, then we can reduce it to around 100 kilometers square, but it is going to force a development of solar PV in riskier land in Arizona to 5,400 kilometers square. So this was the point when I realized that we can use this methodology to facilitate collaborative decision making. But To do that, we need to move from discrete solution space to a continuous solution space. So if you remember the example from before, we had these 4 extreme points. If we take a projection of those extreme points on one of the smaller subspace, which is x-axis here, then all solutions in this line within x1 and x2 are also feasible and near optimal. So if you are a decision maker and you want to choose this value of x, then we can show you how the value of y would change based on your decision. So based on this concept, I am currently creating a tool that will let policymakers set the capacity of different technologies, and it will show us how the capacity of the other technologies will need to change in order to achieve the goal without increasing the total system cost. We can also go a bit deeper, and here I'm showing an example of one of the states where gray area is a big city, and these lines are transmission lines, and red dots are solar PV build out, and blue squares are wind build out. So if a community lives in this area and doesn't want this wind turbine near their homes, then they can show us that, ask us what alternative solutions we have, and we will know the cost of that alternative solution. Or if there are any solar PV near the city which has other usages, then we will know what other options we have. So till now, I have only looked at some of the aspects of these methodologies, and the green ones are what I have studied in detail. I'm very excited to study the red ones here in more detail in the coming years. That is all for my talk. I would like to end the talk with saying that everything around us is connected. We need to allocate certain money to certain